Hello. Today we will be exploring C++ Gold. If you are a student learning C++, then I will be introducing you to a great resource that once learned will allow you to craft simple solutions to an array of common problems. That resource is called the C++ Standard Template Library, commonly known as the STL. It is a collection of template classes that implement the common data structures and algorithms. Now, if you notice on screen, I have a very simple C++ program that shows a simple C++ boilerplate. Your basic IO stream, you're using namespace standard, and a main function. Now, I've given you a short description, and you may already be confused. So let us begin by going over C++ templates. I'm going to give you a problem description. Right. A C++, a C++, X++, right? A C++ program that returns the sum of two integers, two floats, and two strings. Not strings, just strings. The parameters must be limited to 2. But you can write functions as necessary. Right, this is all you have to do. You have to write a C++ program that returns the sum of two integers, two floats, and two strings. Your parameters can be whatever you want, but they must be limited to 2. Write functions as necessary. Now hopefully you pause the video and attempted to build a solution yourself. A typical beginner approach is to write 3 functions, something like add integers, passing in 2 variables, say int x, int y. And all you did was return x plus y. And you did 2 more times, one for float called add float, int x, my mistake, float x, and float y. And again, very simply, using a return statement, you said return x plus y. And finally, you wrote your string called add string, and something like string x and string y, following which you said return x plus y. Very simple. All right. And then you probably did some simple testing where you said add integer. Nope. Add integer. Add int. There we go. And say 1 and 2, expecting it to return 3. Then you did add float. And float, and you did say 1.5 and 2.5, expecting that to return 4. And finally, add string, something like hello and world, expecting it to return hello world. Let us build and run our program. At the cost of a more aesthetically pleasing development area, we sacrifice the efficiency of code blocks. Let's go here. Here we go. We get the output C++ templates and a power, following which we got 1 plus 2 to be 3, 1.5 plus 2.5 to be 4, and hello plus world giving us hello world. Very nice. Let's see. What else can we do? Well, maybe a more intermediate approach would be to take advantage of C++ and the fact that we can overload, that's the one, right? Overload functions. Let's get rid of it being called addInt and just call it add. And I'll also call this one add. And this should work. Let me get rid of that. Add. It would work because C++ is smart enough that it can intuitively understand that despite their two functions called add, they both take a different parameter list. One takes integers and one takes strings. And this should work. Let us run the program again. And there we go. C++ templates and their power, 3, 4, and hello world. Great. Now, let me show you a different way to do it, a far more simpler way. And this is achieved using C++ templates. So, say I have some function int sum. It takes in an integer x and an integer y, and all it does is return x plus y, a regular function. But what if I did something like this? Template, within curly braces, I did type name, and I just pass in some variable name, in this case c. What this states is what follows will be a template, either a template function or a template class. And to use it, I'll simply do this. I'll say t sum, t x and t y, and simply return simply return x plus y. Let us read this above function called integer sum. What this states is we have a function called sum. It takes two parameters, x and y, both being integers, and returns their sum, x plus y, and it must be returned as an integer. All of this is indicated in the function signature. On line 18, however, what we do instead is we use a template. And to use a template, all we do is we type out the word template, and within angle braces, we pass in type name and a variable. In my case, I use t. And what this function states is the following. I have a function called sum, which takes two parameters, both of some type called t, and it returns the sum of x plus y. And it must return it such that the return value is also equal to t. If there's any confusion, let me just go ahead and use a console output. Let me go sum, and I'll pass in 1 and 2, and I'll do an end line. And I should expect 3 from this, right? I'll do cout sum again, and I will do 1.5 and 1.5. And I should expect from that to get an output again of 3. End line, right. I will then do a cout, but this time I will use my template function sum. And the way you use it is you call your function, and within curly braces, you specify the type that you want to use. In my case, int. And I'll pass in values. Let's go 2 and 4, and simply print out an end line. So what this states is, you see where it says integer, go substitute integer where it says t. So now I'll have type name int, two values, int x and int y. Also, return integer. Now you see what templates do. I'll return everything back to what it was. Control Y. Okay. But based on that logic, I can also do this. I can do sum, float, and I can pass in parameters. In this case, let's do 2.5 and 3.5. Well, we know 2 plus 3 is 5, and 0.5 plus 0.5 is 1. So 5 plus 1 is 6. So I should expect to get back the output of 6. Here is 6. But I can take it one step further. No, wait. All right. So now we come back and we do one step further where I do sum. And I can actually pass in a type of string, because why shouldn't we be able to sum strings? And I'll pass in the parameter hello with a space and the parameter world. And again, an end line. And I should expect to get back hello world. Let's run this. I'm actually going to do just end line, end line. Okay. And now I will run it. Okay. So we get the output 3, 3, 6, 6, and hello world. There's something wrong here. 1 plus 2 is 3. 1.5 and 1.5 is also 3. So it seems to be working, right? We get 2 plus 4, which is 6, 3.5 and 2.5, which is also 6, and hello plus world to give us hello world. And this should intuitively make sense. Not the template function, but the non-template functions. Because what we are doing is we're saying pass in a float to an integer function, and it would still work. But for now, let's just get rid of this. Oh, by the way, that only works for some IDEs. Other IDEs may just return the integer part of your float parameters. So you may just get 1.5 plus 1.5 and get the output to be 2 instead of 3. Well, what if we did sum, hello, and world, and we did an end line? Now let's try running it. We get an error. Okay. And we can actually see the error is on line 21. And what that error is basically saying is, why are you trying to pass string parameters to a function that expects numbers? Alright, so now we have a basic understanding of what is templates and why they are so powerful. If we were to just remove this and remove this function, we notice in 1, 2, we can actually shorten this if we want, but let's just say 1, 2, 3, 4, 5 lines of code. Why are you giving me an error here? Invalid operator type char and char to binary operator plus. Are you goofing around? Is it an error from the last build? Let's see. And build successful. Yeah, it was just being a little silly there because it picked up an error from the last time we built. Okay. But as I was saying, in 5 lines, we were able to write a function that can take different parameter types and return their sum, as long as the plus operation is defined for that type. Again, we now see why templates are so powerful. Essentially, templates facilitate code reuse, or the DRY principle. DRY. Do not repeat yourself. Why write many times what you can write once? There are 2 types of templates. In this code, we notice we see function templates, and another is class templates. We use class templates when we define a class that contains definitions that are independent of the data type. which means when I write a method or in a class or a member in a class, I do not want it to be contained or written for only one type. I want it to be malleable. Let me get rid of these and get rid of this as well. And we'll get rid of that as well. Okay. Let us actually create a class template. Consider a linked list. The nodes of a linked list can be integer, float, string. They can be as far as a user-defined type. If I were to do this, template, type name, and I go T, and I create a class called node, which will represent the nodes in my linked list. I can do something like this, public, the actual data in my node, a link to my next node via a pointer, and finally a very basic constructor, tinfo, and data is set to info, and next is set to null pointer. Okay, so let's see what we have going on here. We have a class called node. It takes two members called data, which is of type T. And as you know, because it is a template, T can be changed to a myriad of data types. It also takes a member called next, which is a pointer, which stores the address of some type. In this case, because we passed in node T, it will only take the address of a node of type T. And we also have a basic constructor that sets data to information, and next to be a null pointer. Why are you goofing at me here? Expected a. Oh, yep. Always forget that. Obviously, this is just a node and not the linked list. We will now actually build a very simple linked list. You notice above how I use type name. I can also use class instead of type name. They both have their intricacies, but I wouldn't be too bothered about it. Linked list, spelled wrong. Linked list. A parameter. Now let me see if I'm able to remember some of the basic functionality. We should have a void add function which adds in a node. So I must have data for that node. And if there is no node, then if head is equal to null pointer, my linked list is empty. Head is equal to new node, dynamic memory allocation, putting things on the heap. New info. Basically saying there is no node, therefore any new node is both the head and the tail. Else. I will create a temporary node and call it temp. Now, as you notice, whenever I am referring to a template class or function, I must always specify within angle brackets the type. Let me just run through this in my head. Create new node. The tail of next points to temp and tail becomes temp. Okay, yeah, that's right. And let's just do a simple void print. Nah, let's do traverse linked list. We will create a node that will essentially point to our head so we do not lose our linked list. If I get annoying, autocompletes one more time. While current is not equal to null pointer, then it means I have a node and all I have to do is console output current and data. Just console out white space and current will be advanced to the next node. Now, if you aren't familiar with linked lists and what I'm doing, that's fine. This is just to introduce you more into the nature and power of templates. Okay, cool. Let me come down here and create a linked list. I can do linked list, and I must pass in the type of my nodes. In this case, it'll be integer, and I'll call it my integer linked list. I can do my integer linked list dot add. Let's do 32. I will copy this. I'll do 42 and I will do 52. I will also do my integer linked list dot traverse linked list. I'll create another linked list, but this time of node type string. My string linked list. Dot add. Let's do hello and world. Finally, my string list dot traverse linked list. Okay. And I'll do an end line. Okay. Let's see if everything works. There we go. We get out the values 32, 42, and 52, and hello world. Our linked list works. And because it is a template class or a class template, we can use different data types in our linked list. Cool. We are understanding more and more as to why we would want to use templates. Okay. Now that we have an understanding of C++ templates and why we would want to take advantage of their functionality, let us return to the standard template library. Let me ask you a question. Why do we write programs? We write programs because we want to solve problems. And we do this by writing a program that takes some input, does some processing or some manipulation on that input, and generates results, and hopefully solves the problem. To do that, however, we need to store data in memory, access specific data satisfying a certain condition, and write algorithms that operate on that data. And there are different types of objects that serve the purpose of storing data, such as an array. Let's create one. So integer array, let's go size 5, and let's go 1, 2, 3, 4, and 5. And that creates an array. If we have a predefined size, Then we can create an array. And it's a random access. So I could do something like array at position 0 and get whatever value is stored at position 0. And it's also modifiable, so I can change the elements. We also have linked lists to store data, as the ones we created up here. If we do not have a predefined size, and we don't mind walking through the list to find specific data, we can use a linked list. If we need a first in, first out data structure, use a queue. If we want a last in, first out data structure, we can use a stack. Now, back to the STL, or the standard template library. It has 3 main elements. STL has 3 main elements. That being containers, iterators, so iterators, typically traversal, and finally algorithms, operations on data. Simple, right? So the standard template library has 3 main elements: containers, iterators, and algorithms. And I left my curtain open and the sunlight is piercing my eyes. Alright, so something else about containers is that they are class templates, just like the one we defined above for our linked list. And also iterators are class templates. Let's begin with containers. Oh, by the way, I have linked in the description below resources that you can use to further your skills in C++ using the standard template library. So, we saw how we can create an array in C++. So, integer array of size 5, and say I had of size 5, and say I had the values of 1, 2, 3, 4, and 5. Cool. And I can do something like array dot, okay, I get nothing. Here's a question: how do we traverse this array? We can do for int I equal to 0. I is less than 5 because I know how many elements are in that array, and I can simply walk through that array. Array at position I, and I can do it end L. I'll also just go above and get rid of these for now. No need for them. Wait, no need for them. Why am I commenting them out? There we go. And if I run this program, I get 1, 2, 3, 4, and 5. Very nice. However, there are some drawbacks here. For one, arrays cannot grow. Once I have a set amount of elements, I cannot exceed that amount. In this array, I have 5 elements. I am not going to be able to add another. Also, what happens when I don't know the size of an array and I want to traverse it? A simple issue, quite hard to get around. So let's go back and talk about standard template library containers. A container is used to store data of various types. And that is why we use class templates. Something such as vector, we'll pass it an integer because we want to store integers, and we give it a name. Let me actually make it general. So something like container, type, and then container name. And that is how you will create a container using the standard template library. Containers can be further subclassed into 3 categories. Adaptive containers. These containers have a very specific use case, such as stacks and queues, for last in first out and first in first out reasons. Sequence containers. These are containers that are made such that each element in it has a specific position, like an array, 0, 0. And then there is associative containers. Elements in an associative container are automatically sorted to some ordering criteria. Before we go any further and write any more code, there is something we need to do. And that is I need to plug my laptop in. Oi. Let's see. There we go. But yeah, joke aside, we need to understand something. All containers serve the purpose of storing data. It should not be surprising that these containers will share certain operations. Now, when I say operations, I mean algorithms. When I mean algorithms, I mean, remember, containers are classes, classes have members and methods, and these containers will share some members and methods. A vector is a data structure that manages its elements in a dynamic array, which means, like an array, all the elements can be accessed randomly, but unlike an array, we can have our vector grow to accommodate more elements. Now, to use a vector, we have to include it by using the include statement and referring to its header file. In this case, it's just vector. Very simple. We now have access to the data structure called vector. How do we create it? Well, it's quite simple. Say I was creating a string, I would pass in the name string to refer to the type, and I will give it a variable name followed by some value. Right? That's how you create a string. In a similar manner, we create a vector by passing in the type, which is vector, and within angle braces, we refer or pass in the type that we are going to store because it is a container. In this case, I will pass in string. And I'll just call it string vector because it must have a name. There we go. And because this is a class, this uses the default constructor. It creates an empty vector called string vector, which can only store types of type string. Objects of type string, excuse me. I need something to drink. Let's do vector, integer, and let's call it numbers. And this time I'll do 1, 2, 3, 4, 5. I'll then create a vector of characters. So I pass in char, and I'll call you characters. Characters. And instead of using the default constructor, I will overload the constructor, which actually allows me to pass in the element list within the braces, or should I say within parentheses, ABC. That's good. Now notice, we are experimenting with constructors here. We have the default, we have this one overloaded constructor. This one also uses the default constructor, but then we immediately assign it the values 1 through 5. Okay, let's do another one. What if I wanted to create a vector of integers and I'm going to create it called 100 elements. Problem with that name. 100. Nah, I'm just going to call you a lot. And all I am going to do is pass in a size. And that size will be 100. What this does is, it's a constructor. It's not saying create a vector with the value of 100. No. What it's saying is create a vector that is empty, that has allocated space for 100 elements of type integer. I'll show you one more useful constructor. vector int, let's call it row. I will pass in the element I want in it, not the element I want in it, I mean the number of elements. In this case, I want 10 elements, and I want them all to be assigned the value 0. So this constructor takes in size and an element. And it says, create a vector of size, in this case 10, and allocate all those 10 spaces to be the value 0. We can take it one step further. I want a vector of a vector. So it's a vector containing a vector, and the inner vector must be a vector containing integers. I'll call it table, and I want 3 rows, and I'll pass in row. This creates a 3D table, or should I say 3D container. Now you may be asking, do you have to learn all of these constructors for all of the containers in the standard template library? No. A lot of the data, the members and the methods of the standard template library are common across a lot of the containers. So once you know one, all you have to do is adapt that information to use it for another. We now know what templates are, why we use templates, the 3 elements of the standard template library. We know that there are 3 types of containers. We also know that a vector is a sequence container. But how do we access the elements in a vector? Without this, how would we insert data, delete data, and modify data? Now we come back to classes. If you have an understanding of classes, you'll be aware of members, that being the attributes that define an object, or the characteristics of an object, and methods, the functions that operate on the members. A vector is simply a class, and therefore it has members, but more importantly, it has methods. So we could do a console output, refer to our vector, in this case let's refer to numbers, and we can call in one of the many functions. So I can do dot access operator, and I can call in a method such as at. And at takes an index, which is a position, in this case 0. And I'll do an end line. Let me get rid of this up here. And I should get back the value 1. And there we go, we get back the value 1. Now, not to beat a dead horse, but as I said, because the standard template library has many containers, these containers share methods and members. The at method is a common one, therefore if you have any container, you can simply do container.at and pass in the index to get a value at a specified index. I believe at does bounds checking, maybe I am wrong. We also have another, we can do numbers.end. And now let's do an end line and run this. Link to standard output. No, pretty much. Oh wait, because this should pass, actually return an iterator, right? So, not to jump the gun here, but it will be vector integer iterator is equal to, let's just call you I. Right, if I have to do cout, dereference I, and then do an endl, that should be it. Right. Oh, did my run button disappear? Where'd you go? Come back here. Yeah, you did disappear. Now you're back. Nice try, VS Code. -141, so it should be 1 minus. So what the .end method does, it returns an iterator to the last position of a vector or a container, but not the last valid position. A better one would be to look at front. Numbers.front. No suitable constructors. Oh, my mistake. It's numbers.beginning, right? Right. Yeah. There we go. And now we get 1 and 1. That makes sense. Now, let me show you how we can use this to traverse a vector without knowing the size. We can do for int I equal to 0, as long as I is not equal to, and this is a great part, all we have to do is pass in the vector name, in this case numbers, and refer to a function called size. And the size function will always return the number of elements within the vector. Therefore, we can do cout I and L numbers at position I. Yep. And there we go. 1 all the way to 5. And now you see how we were able to overcome the problem of an array. We do not need to know what the size is beforehand to traverse it. We can add elements to it. We have access to methods and members that are previously not accessible in an array. So all a win. All positives, all pluses, all net positives. Remember, earlier I said the STL is composed of 3 things: containers, iterators, and algorithms. Iterators are pointers. Now we talk about them. The syntax to create an iterator is quite simple, and it will not change regardless of the type of container. It's container, container, type, iterator, and then name. And that is how you create an iterator. If we wanted to create a vector iterator that only considers integer vectors, we do this: vector, integer, resolution scope operator to grab the iterator, and then let's do numbers iterator. And I can end the line. Now let me show you how to iterate through a vector using an iterator. I can do for, I can call numbers iterator. I can assign it to be nums.beginning, which points to the beginning of a vector or actually any container. And I can say, as long as numbers iterator is not equal to numbers.end, remember this gives you not the end of the vector, but rather one position after. And then I do plus plus nums iterator. Because this is a pointer, we do plus plus in the start. Cout, this is actually numbers. Yeah, cout, dereference number iterator. End line. I should get this output again using this code. And there we go. 1, 2, 3, 4, 5, and again 1, 2, 3, 4, 5. Cool. And what's great is you see this beginning and this end function. This is not unique to vectors. It is applicable or accessible to all containers within the standard template library. So regardless of which container you use, you can always use this method with slight modifications to account for the unique container you are working with to traverse all the elements within the container. Let me show you something. We notice that containers in the STL share many aspects. Once you learn the container in general, you will have an understanding that you can adapt to suit your needs based on the container you are using to solve a specific problem. Let's bring this here. This is lead code question 4, a hard question called median of two sorted arrays. Excuse me. Median of two sorted arrays. We have the problem description. Given two sorted arrays, nums1 and nums2, of size m and n, respectively, return the median of the two sorted arrays. However, if we let me just close that. Notice here on the right, even though it says arrays, we are actually given two vectors, or should I say reference to two vectors. And vectors are probably the most common container you will come across. Just due to the fact they are simple to work with, they are dynamic and they are random access. Now, we need to write a function that returns the median of two sorted arrays. I have solved this. My best submission was 12 milliseconds with a memory of 90.3 megabytes, beating 100% and beating 97.3%. Now, if we look at my solution, it's quite simple. If the size of my first vector and my second vector is 0, this means that neither vector contains elements and therefore their median is 0. If this does not hold, then I create another vector called nums3. I know, very nice naming scheme. I use a function that is common between all containers called insert, which does what it says, it inserts values. And I use one of its many forms. I pass in the end of nums3, and I want to fill in all the values from 1 and all the values from 2. I then use an insertion sort algorithm up here, which I created myself, to sort nums3. I then check if the size of nums3, which gives me the number of elements in it, if it is divisible by 2, then I have an even vector. In this case, to find the median, I need to find the position, so I do that by writing this part here. I then take x and y, just names, nothing unique to them, and I return static cast double of x plus y divided by 2. But if my nums3 vector is of odd length, in that case, the median is very simple. All I say is median position is the size plus 1 divided by 2. And then I return nums3 at median position minus 1. And that's how you can use a vector to solve problems, all provided to us via the standard template library. Now let's hope this part recorded. Now this question has 6.4 million submissions and has been accepted by 2.5 million submissions, with an acceptance rate of just below 40%. And we were able to solve it in less than, if we go here at 47 minus 21, giving us 26 lines of code. And by the way, we don't need to use this insertion sort. If you want, you can use an insertion sort that also exists in C++ standard template library. Nope, I believe it exists in the algorithm header file. Yeah, it should exist there. I'll close that. Let me go up here. I will introduce even more containers. Let's do a deck, and let's do a list. I don't think I'll use deck, but I may use list. Okay. So regardless of the container being used, once you understand the purpose of a certain function, such as the begin and end function, we can always adapt that understanding and apply it to a different situation. There's a lot more we can go over, such as operator functionality on containers. So you can actually take two containers such as, let me see, we can take, let me see, cout numbers equal to characters and L. Is it not equal to? Am I being mistaken? If numbers equal to characters No mattress operators. No, something wrong going here. Let me just try to do a little active debugging and see what's going on here. Because if I am not mistaken, I should be able to do that. Unless I am confusing myself. Let's see. All right. Okay. Let me look at my old code and see what's going on. Interesting. Have I fooled myself? No, that cannot be the case. Oh, that's why. Copies the elements of one. No, yeah, that should work. Vectors return true if container A is equal to container B, false otherwise. Let's try doing vector int numbers 2, and I'll just call you 1, 2, 3, 4, 5. Okay. Alright, so it only compares containers of the same type. Alright, so the way it works is it returns true if container A is equal to container B, false otherwise, on the premise that container A and container B are both of the same type. Cout numbers equal to numbers 2 end line. Oh, but like, what if I were to do this? There we go. A. And actually, this will just default to 1, so I should make it specific and say that true 1, 2, 3, 4, 5. Right. I was both right and wrong at the same time. There we go. True 1. That's cool. We also have not equals to. We have the assignment operator, so we could do vector. Let's do string copy vector, and we can actually pass it in another pre-existing vector. And this copies all the elements of string vector into your other vector. Cool. We are furthering our understanding. I need something to drink. I feel like this video has been going on for a while. When I am done, I'm going to grab food and probably watch a horror movie. More accurately, I will grab food and spend an hour looking for a horror movie to watch. There just ain't anything good releasing these days, people. To my chagrin. Alright. Now, it's not enough for me to show you one container. I will show you one more. It will be a sequence container called a list. Lists are actually implemented as doubly linked list. What is a doubly linked list, you asked? Well, my confused friend, you notice how in a linked list here, we point to the predecessor? No. We point to the successor, the one after, yep. So in a typical linked list, we point to the successor. But in a doubly linked list, every node points to both its immediate predecessor and its immediate successor, which is a nice way of saying the node points to the element before it and after it, except of course for the first and last elements, because that would be impossible. So let me see here. Where is my list? There's so much more I want to show you guys, but there's so little time, and I tend to ramble. List, because it's container again, we have to pass in the name, the type, which is list, and the type you're storing. In this case, it is a list containing elements of type integer, and now I pass in the name, list 1. And I'll just pass in 1, 2, and 3. I'll do another list of integers again. I will call you list 2, and I'll pass in 4, 5, and 6. Now, I'm going to do list 1 dot remove if, and I'll say even, and then I will just do, no, I don't need to do that, I can just do that. I have my doubly linked list called list1, and I'm calling some function called removeIf, which should be intuitive. Removes all elements satisfying a predicate. In this case, my predicate is called even. What is even, you asked? Well, guess what? I haven't even written it yet. I'll come up here and I'll just do Boolean function called even, and it should take in some const integer reference called value, and simply return value divisible by 2 is equal to 0. Right. So what this should do is it should look at my list 1 and it should remove all even elements. And if I were to do 4 int I equal to 0, I is not equal to, and I do list 1 dot size, because I know size exists, and I do I plus plus, I can simply do cout list at position I and L. List 1. Right. No operator matches these operands. So what I would have to do is use an at. Okay, let me try doing. So that doesn't. Oh, interesting. You do not have an at to define for you. That can't be the case. Is it because you are doubly linked list? No. It is because you are linked list. Dot assign back end. Let's do front insert merge. Are you challenging me to use an iterator? Oh no, who could have foreseen that? In that case, I do list integer. Refer to the iterator and I'll call it list iterator. And I'll just do that. I can do for list iterator equal to list1 dot beginning, as long as my list iterator is not equal to list1 dot end plus list iterator, should I say advanced list iterator, and I can do a console output list iterator dereferenced end L, and let's run that. And I get back 1 and 3, which makes sense because removing even will only remove the value of 2. Ain't that cool? Now, we've been creating iterators, but let us talk about them. It would be good for you to know that there are 5 types of iterators. That's right, there are 5. We have input iterators, which have read access. We have output iterators with write access. We have forward iterators, which combine both input and output iterators. We have bidirectional iterators, which are forward iterators but they can also iterate backward. And finally, we have random access iterators. Because I've showed you how to use iterators, I will not go too much in detail because that will be robbing you of the experience of banging your head trying to figure them out for yourself. Trust me, I've spent many a day, many a night in a cold sweat trying to figure out why my iterators are not working. Now let us have a brief discussion of associate containers. As I said earlier, the elements in an associative container are automatically sorted according to some ordering criteria. The default is less than. You, the user, can override that, however. Let's talk about one called a set. And a set must contain unique values. In other words, it will not allow you to store non-unique values. And because it is a container, I know I pass in the type called set, the type it will store, in this case integers, and I'll pass it some name, my set. This is a default constructor. My set is empty. I'll create another one, set. I'll pass it an integer, but I can also pass it something else in the angle brackets. I can pass it in a comparison. C++ has a built-in one called greater, which it itself is a template, so it takes a template argument. And I can call it another set. It's also empty. If you want to insert values in a container, you do the container name dot insert, and you pass in the value you want to insert. In my case, 16, and I'll do two more, 16, 12, and 1. I will then do copy, which is available because I'm using the namespace standard, and I will do my set dot beginning, my set dot end, and if I do ostream iterator, am I spelling you wrong? It's ostream. Oh, that's why. Ostream iterator, nope. Ostream iterator, and let's do you an integer, and let's do console output and a blank. You are undefined. ostream underscore iterator integer console output. All right. So you know how console output is what we use to write out to some output stream? Well, in this case, I'm doing the same thing, but I'm doing it in one line. This states, whatever is in the starting of my set, all the way to the ending of my set, write it out to the console output. But don't just write it out blankly, write it out with a space in between every element. Now, I want you to think or guess what the output will look like. Will it be 16, 12, 1? Will it be 1, 12, 16? Will it be 12, 16, 1? I get back 1, 12, 16. And the way it's done is 1 is less than 12, 12 is less than 16. Because, as I said in default, associative containers use the less than as their comparison operator. But because I passed in this little neat function, I can do this. I can do another set dot insert. Let's do 1, so many ones. Only one will exist because it is a set, does not allow unique, non-unique values. Let's do 1, 2, 4, 15, and 100. Now, if you notice, this is actually in appropriate order for our mySet object because 1 is less than 2, 2 is less than 4, 4 is less than 15, and 15 is less than 100. And if I just copy this, if I paste it here, and if I do another set, and now if I run U, would you look at that? I should actually go ahead and print a new line before I get all excited and line. There we go. One less than 12, 12 less than 16, and the next one, 100 greater than 15, 15 greater than 4, 4 greater than 2, and 2 greater than 1. All accomplished through templates. And finally, let us talk about algorithms. We have been using algorithms: insert, begin, end, remove if, even. They are algorithms that are specific to certain containers and algorithms that are shared amongst all the containers. Common ones are find, sort, merge, and they are typically found in a file, a header file, appropriately called algorithm. Again, look at the resources provided in the description for a deeper understanding of these concepts. There are 4 types of classification of algorithms: modifying, which modify the elements of whatever it is being used on; non-modifying, typically for searching; numeric, because they typically, well, they only work on numeric values; and then there's a special one called heap. There's a type of algorithm that is more general called generic algorithms. Let us write code that uses a generic algorithm, such as a JSON find. Let me create a vector of integers, and I'll call it nums. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 8, 9. I'll then create a vector integer, but I want an iterator, so I do that, and I'll just call you I. T, it. If I access this algorithm, which is just a function, in the algorithm library called a JSON find, I can pass in the starting space. So in this case, I want to start from the beginning of nums, and I want to search all the way to the end of nums. And I want to determine if there are any 2 elements such that the element is the same and it appears directly after another element that is exactly it, return the position of that element. If not, then it will be set to nums.end. Cout. Okay. My ears are actually starting to hurt. Position value 8. Would you look at that? Cool, isn't it? Imagine you having to write this function yourself. You don't need to. Go to the standard template library and use the algorithms header file. Now, we conclude our video here. It may appear as we have learned a lot, But in reality, we merely scratch the surface of what is possible with the standard template library. You should take some time and explore the STL. I provided resources in the description. And when I say explore the STL, I mean actually use it to write code, don't just read it. To reiterate, the STL provides data structures and algorithms that serve as solutions to reoccurring problems. An important resource for all C++ developers, and one that I wish I had learnt much earlier. This is LeetCode problem 125 called valid palindrome. A very simple way to determine if a given string is a palindrome is to simply use a stack. And that is what we did here. 6.2 million submissions, 2.9 have only been accepted with an acceptance rate of less than 50% for quite an easy problem. If you go to the STL and you learn about stacks, you'll be able to implement simple solutions to such problems very effectively. And that is all. Bye bye.